Welcome to episode 30 of Roid Rage. Today we have Wesley back on the podcast. Last time you were here, this is not your first time. Last time you were here talking about vibe testing. This is going to be slightly different. We're going to have you talk about those giant things that stick out from the side of the spacecraft and play a fairly important part. So that is solar panels. So what I'd love to do today is let's scope. You worked on the solar panels for Odin. And testing on them. Yep.
Totally going to make that your fault. I was like, oh, really?
Just to be clear, testing. So it's not your fault that it didn't deploy.
Sure.
Yeah.
I mean, it's 100% Wes's fault.
Well-
we have a full blame culture here at AstroForge, and I blame Wes.
Super helpful. Yeah.
Okay,
Okay.
but we don't actually know it deployed. I know Matt knows it didn't deploy.
It didn't
Yeah.
deploy.
That's fair.
But that whole root
Allegedly.
cause analysis,
Allegedly.
engineering
Yeah.
approach.
Yeah. Okay.
We don't-
Or the pictures of it from Athena that show that would not deploy solar panels.
All right. Either way.
There's some room for disagreement there.
So you worked on Odin solar panels. You've been pretty integral into the redesign on Deep Space 2. And I'm going to use this as a reminder that we have renamed Vestry to Deep Space 2 just to keep it simpler. So when we keep saying Deep Space 2, you know what we're referring to. We're working on the redesign. So I guess let's start from the top. Before we start on Deep Space 2, remind us what was on Odin and why we made some of those choices.
Yeah, so Odin was 2 wings, PCB-backed solar arrays. So the PCB is just kind of like any type of electronics board, essentially the same thing, just a little bit bigger with solar modules laid on top. And if you've ever seen a picture of Odin compared to Deep Space 2, they are a lot smaller. And we had one HDRM, that's a hold down release mechanism. That's what holds it in a stowed configuration, right down the center of each array. And then when they deployed, they were not a traditional Z-fold like you would see on every kind of modern solar array configuration on vehicles. They actually did a full unroll type of deployment. So the outer panel was on the inside, and then they would unfurl, which led to a larger shock at the end of deployment.
Got it. What, I know you did a lot of testing work on there. You weren't part of the original design. Vision is history.
Still your fault.
Still your fault, even though it wasn't your design. Why do you think we chose that design, and what choices are you what choices are we rethinking as we go into Deep Space 2?
So at the time, we were coming off of a bus that was built out of house, and I think we were just going for speed. And there were companies such as Pumpkin that have designed solar arrays before, so we went for a known manufacturer that has built a solar array for a bus before and has deployed it in space. So that's why it was designed out of house, tested in house. So the DASA, which is the deployed what's that?
This is why we don't use acronyms right here. The solar panel turning thing.
Articulating solar array. Yeah. For deployable articulating solar array. That
Even
was
I can't argue
purchased.
with that one.
That was purchased from Pumpkin, and
Okay.
then the modules themselves were purchased from Pumpkin with the spring configuration, and then the HDRM was purchased from D Cubed.
Okay.
So we combined a couple things together to make what was the overall system of the solar array.
But that choice on Odin really came down to time. We could buy the Pumpkin solar panels, the 3-wing configuration, which produced 90 watts per side. By the way, those are triple junction cells that had glass over them, right? So they also were not super mass effective, but they were available. And also the power conditioning units from Pumpkin that fit those panels. There was other panels available, but then we would have had to bring the power conditioning in-house. And in the 4 months we had from when we started to when we had to go vibe test, I didn't think we were going to build a power distribution board and a power conditioning board and plug in some new solar panels. So the fact
Now,
that
this is one of the rare episodes that I think I would say, Matt, you were right.
I'm pretty sure I'm always right. I don't actually know if I've ever been wrong.
I'm pretty sure there's at least 2 people out there with AstroForge t-shirts that would disagree with that statement.
Moving on.
All right. So it sounds like for a lot of Odin, the main constraint was speed. So we actually didn't do a whole lot of like core design of the solar panels in house, right?
Of the solar panels themselves, no.
Okay, got it.
Right. No, I think there's a little bit more detail we should add here with it is that we also didn't fully understand how temperature variation applied to the pumpkin cells. So we made the assumption that we were getting 90 watts per cell out on those. I'm sorry, 90 watts per wing as input to the power system. That was actually not true depending on the configuration, both with temperature and fluorescence we were seeing in space. So that was inaccurate, and we probably should have added more margin on top of that. We also didn't expect for what you said, which was they were printed on these thin plastic elements, which caused a really difficult time when vibing them and really made us have to work with the deployers a lot. So obviously we know, although Robin hasn't admitted it to himself yet, he will probably within the next 3 to 4 months, that the panels didn't deploy. It's also really hard to look at that and understand. Like we had a lot of problems with deployment, both excessive deployment and not excessive deployment in testing. That's actually why we went back into testing on the configuration of the D-cubed. And it's important to know that the D-cubed was a shaped metal alloy. So when you apply a voltage and it heats up, it changes shape and releases the panel. It was not an explosive charge. It's kind of two different ways to do it. And so, yeah, I think those are kind of like, I don't know if there's any other details I'm missing of these panels, but there was a lot of details to these panels that because we were building so quick, we kind of probably overlooked more than we should have as we went out to go build Odin.
Yeah, it was a lot of learning as we went, especially after we got the full system integrated, which was pretty late into the process.
Yeah.
So aside from sort of the vibration testing, like what else were you testing for
Yeah,
on Odin, and how has that expanded what you think about testing for Deep Space 2?
So we didn't test articulation a whole ton in a deployed state.
Okay.
So now we have this huge fixture that's standing up and it has the whole solar array hanging, and you could test the motor and make sure that you can see what stalling looks like, what homing looks like, everything like that.
What are stalling and homing?
So homing is you drive the motors to their maximum limits and then you center them to a point where you know what the state of the solar arrays are and where they're pointing. And then stalling is we have these hard stops to allow for that homing process to take place. And when it pushes against these hard stops, it senses a resistance. And then you could say, okay, flip the other direction or stop driving.
Got it.
Yeah.
Got it. So testing more for articulation on this set of
Yeah. And then
panels.
we tested without the arrays attached.
Yep.
We didn't ever test them with the arrays attached because we didn't have fixtures set up for that. Alongside the speed at which we were going, that kind of made it difficult to build up all those fixtures. And then the other one is when we had the power system fully built up and integrated in the vehicle, we ran into this error where if we deployed the array and we set it on a stand and opened it up to the light, we would see the power system brown out. And that had to do with our current limits and setting that configuration correctly. So took a couple of those lessons into designing the power system for this next one.
I'd say it's also really hard to test the power system. One of the things we did is we rolled it outside into the sun, and then we had to make sure the sun could like see between both buildings and it wasn't super cloudy, and we're trying to time it. And like, if you get it wrong, you have to wait 24 hours. And the first time we did it, it was really difficult to go test this in a way where you could actually get some real scientific evidence this was going to perform at an adequate level when we were in space.
Yeah, and solar arrays.
So I bought lights.
Yeah. And solar arrays, if they get a little bit of dust on them, they lose efficiency pretty quickly. So, we bought lights and we're building a fixture to make sure.
Currently stuck in Compton. We're working on it.
That's not that far away though.
No, but it's at a facility.
Compton is another world away.
But I'll have to break in.
It's like 12 miles away.
It's another world.
Okay.
You could run that.
I ran through Compton, remember?
No, I
no?
Why would you
I was
remember?
not with you.
All right. I thought you were with us when I ran through Compton. Never mind.
I don't know.
What the hell are you talking about? I'm talking about lights for our solar panels, and you're talking about taking a jog.
Okay, so we have a better sort of suite of tests that we're going to put these new solar panels through. I guess start from like the high level descriptors, just so we can remind people like what are the differences in size, mass, and power between Odin and Deep Space Two from a solar panel perspective.
Yeah. So in terms of size, Odin's solar arrays fully deployed were around 2 meters long, and then they were, I think, like a third of a meter wide.
Okay.
These ones are each panel in the stack up, and we have 3 panels on a wing, are like a meter by a meter. So we
Okay.
have 3 meters long, 1 meter wide per wing. So
Okay.
that puts us, pretty dang wide, 6 meters across with just the wings, and then a meter body in between. So size wise, we're getting an order of magnitude larger. And then in terms of power, I believe, I can't remember the exact power numbers for Odin, but
Pretty
would
sure Matt just said it was 90
It's 180 watts total with
per
Odin,
wing.
but that's if you look at in its coldest state that
Yep.
we would go to, right, with full sun.
Yep.
That we're looking at 1 AU, what 1 Earth distance from the sun, which is equivalent on Deep Space 2 to 2,177 watts.
So almost another order of magnitude.
another order
yeah.
of magnitude
Okay.
larger.
Okay. And
Cost the order of magnitude more too.
Yes, they definitely are.
Yeah, we're going to work on that for
Yeah.
Deep Space 3.
so yeah, to walk us to where we started to where we are now, and like how much of this we've done in house versus brought from external vendors.
Walk us through the design spiral.
Okay. Yeah. So-
Matt, you're not authorized to use that terminology.
Sorry. Jumping in for you, Robin, while you're over there eating cheese.
Cheese is so underrated.
Really is. My wife yelled at me the other day because she saw me eating a piece of cheese just like a carrot, and she was like, "That's an improper way to eat a piece of cheese." And I didn't realize that there was like a proper way to eat string cheese. I thought anyway was acceptable.
I'm pretty
but
sure
turns out not.
ringuette is French, right? So you're allowed to eat cheese however the fuck you want. We have to follow the French. Isn't that how it works with cheese?
It's how it works with me. I mean,
Apparently.
Okay.
right.
Back to solar panels.
Yeah.
Yeah, so in terms of we wanted a lot less mass per unit of power, we went straight for the lightest things that we could possibly think of. We just went, hey, let's make a carbon fiber frame. And how do you make a carbon fiber frame as light as possible? Well, you put 1 ply of carbon fiber over that and essentially make a drum head. And then how do you make that work with a module? Well, you have to get a flexible module because that drum head is going to bow as you throw it through vibrational, like environmental testing. And so we pretty much went through, we did a structural analysis, came up with a frame that was just over 40 hertz, and then stuck some modules on it and took it to testing. And at testing, we pushed it above the limits that SpaceX requires, and it ended up having a peel failure. We just wanted to push it all the way to its structural limits.
What's a peel failure?
So basically, the carbon fiber layer running across that picture frame pulled off of the frame itself. So think of a canvas on a picture or on a.
Yeah, so you hit the drum too hard and it peeled off.
Yeah,
Yep.
essentially.
Yep.
And so that would mean just to make sure that's structurally sound, we would throw some washers over the top of that. And all of this was just starting to add mass as we kept going. And, you have some doubler plates that would allow it to stiffen.
Yep.
And one day Matt came up to me and he said, hey, have you looked at like the comparison between this and this, what I see everywhere else, which is a sandwich panel? And I was like, I have not looked at that in a while. And so went back and looked at the difference between a carbon fiber face sheet, aluminum honeycomb core sandwich panel, and the frame that we were working on, and it came out to be a good chunk lighter than the picture frame was at the time. So we started looking for suppliers for that, although I think we may be coming on an inflection point where they're becoming quite similar.
What do you mean by that?
So a problem that we found recently with the electric propulsion system is carbon fiber has these microscopic hairs that come off of it that create these point.
It's conductive.
Sure. Yeah. You can arc from your EP system to the carbon fiber itself, and so we need to cover them.
Just to give people like, what's the distance that you're arcing there? Because those aren't particularly close, right?
They're like a meter away.
Okay.
It's not super far by any means, like half a person. That's how we're going to measure that, I guess.
So we just went from metric. We went ahead and skipped over and just went
people
to
measurements.
people. Yeah.
Yes.
I actually
Okay.
think we should just do all of our spacecraft measurements in people now. That's a quarter of a person over there. Yeah. Okay. So we had a problem because it was arcing, because it has a little.
Well, let's be
fibers
clear.
off
It hasn't arced yet.
There's a
Okay.
potential to
potential.
arc.
Yeah.
Okay.
Let's just,
And so
we'll have the arcing episode when we do arc.
Yeah, and so we were suggested to cover these face sheets, and so we have to layer them with a film of some type. And the modules themselves can short with carbon fiber, so we already had to cover that side with an insulative material. So we're putting Kapton and we're co-curing that to the carbon. So when they press all these sheets together, there's an epoxy resin that bonds all the fibers together. You can also just lay Kapton straight on there and cure it all as one. So you don't have that risk of peeling like we did with the picture frame that we did before. So we'll have the Kapton on one side, and then we're gonna do another layer of essentially a higher grade of Kapton on the other side. So all of this adds mass, and you need to go back and forth and see.
And for our
which one
listeners,
makes sense.
Kapton is just really expensive Scotch tape. Basically.
Yes.
That you smoke around a lot because it's got that yellow smoker's tinge to it. Really adds to the space.
Okay, you're like 0 for 2 on this episode.
She's got like that old school
There's-
Reno vibe, just like
old
everything's.
school.
Yeah.
It's like you went to a casino in Laughlin. Exactly.
There's also
Where?
black Kapton.
Why don't we spend more and get black capped on?
That's conductive.
Please don't buy the conductive Kapton, Wesley.
We might for the backside.
But we're actually skipping.
Well, that's different.
We're skipping part of the design we did because we actually didn't start out with a window frame or a panel. In the very early days of looking at what Deep Space 2 would be, we actually started really, really highly considered doing rollouts.
rollouts, yeah.
Right? Missions like DART,
Mhm.
the ISS have these big rollout panels that allow you to keep it up and roll it out to make it. DART is still to this day the highest kilogram per watt spacecraft ever flown. That's actual scale. I'm sure some CubeSat beat it, but that's not what I'm counting at a full scale spacecraft. We looked at rollouts. The problems we had with rollouts is we didn't think we could actually secure the material in time from any manufacturer. We didn't believe anybody was ready to produce it at the resolution or the efficiency we needed.
What's the ballpark efficiency that we need?
Panels are 33% efficient, I believe, right?
Yeah.
33% efficient. We looked at 2 brands of rollout panels. One of them was in the low 20s. One of them was in the low teens.
Okay.
And both of those just mean, if you're 1/3 as efficient, you could translate that by building the solar panels 3 times as big.
Yeah.
And that's just a huge mass consideration we go to, even when we looked at the rollouts. They're hard. A lot of companies are working on a lot of cool tech to make rollouts different. We just didn't think anybody was far enough along. And I think at the end of the day, we're talking about going into high rate volume production of spacecraft. You also don't want to pay for somebody else's NRE that then you don't own, that then you have to continuously buy. And so this is where the challenge lies with using any kind of rollout.
Got it. Let me take this opportunity to say, like, we're not the only ones who have a solar panel problem. Most every other spacecraft has a solar panel. Like, how much do we look to what other people are doing versus just try to learn the lesson?
You're
our
asking
way?
how much we copy?
I copy, borrow, infer. Like, we can use a lot of verbs here.
Yeah, so I mean, this is kind of why Matt had come to me and asked, why are we not doing sandwich panels, right? Because he's looking at pictures and he sees that everybody's doing sandwich panels. The big difference is we have an EP system on a really tiny bus. So we have really massive solar arrays for how small we are. Whereas if you look at a lot of other buses with electric propulsion systems, they tend to have a wing or a panel that's as big as their bus is. So it's super easy to secure. Whereas for us, if you've ever looked at a picture, our solar arrays are going way beyond the bus itself. And there's this big cantilever that's going to cause these structural problems that that we're seeing through analysis.
But we do steal a lot. I mean, we are the China of spacecraft, right? Like, I want to steal everybody's IP that I can and use it to our advantage.
What Matt means to say is he would like to utilize the industry lessons learned.
Yes. And look
Thank
at
you.
pictures and see what they do. And that's it. Like, it's really easy to tell what is, these companies, we can look at something like the Psyche mission and look at their giant solar panel arrays and realize Maxar spent a shitload of money doing a lot of trade studies and a lot of testing trying to figure that out. Maybe they were onto something. Maybe we should look at how they did this deployment, how they thought about it. And as you start to iterate and build these, you start to understand why they made the decisions they did. And so it's really that basic, right? Like, other people have done this before. We're not doing anything new. Let's go borrow from it.
Are there any of the types of solar panels or solar arrays that we could have borrowed from? So you mentioned rollouts.
Rollouts.
And we'll look at rollouts again. I mean,
Yeah.
technology changes pretty fast. So
We just need the film to be in production that we can buy at a reasonable cost.
Yeah.
Right now, rollouts are done by, I think Northrop makes the rollouts.
yeah, there's a startup that's
There's a couple of them.
that
That are
are
doing
that are
thin film
doing it,
rollouts.
and they're almost there. So
We
we'll
need to
see.
wait till one of those startups get to the point where we think we can actually procure it at a reasonable volume. Until that, we can't afford Northrop rollouts.
Yeah. And the lead time is extremely long on all of them. So, especially as we try to move quick, you could think about it in advance, but if it's not going to get here in time, then we're not going to use it.
Yep.
So, there's the rollouts. We've seen sandwich panels.
Yep.
We've seen PCB backed, and we tried the picture frame, but we found a lot of complications with it, and
Got
keeping it consistent was another different problem. So that's kind of the main types of solar arrays that you see out there.
So you touched earlier on how we deployed panels on Odin. How are you thinking about the deployment of the panels for Deep Space 2? And how is that changing?
Yeah, so we're no longer going with a shape memory alloy HDRM, hold down release mechanism. We're going with a pyro hold down release mechanism. So it's a single time use. Once you fire it, you have to swap out the entire thing, which is expensive, but they're much more reliable and tested out there. So
It's really a break wire, not a pyro, but
yeah.
that's fine. You're not the RE or anything on it. It's fine. It's totally fine.
Go into some details what it is, Robin. I mean,
Yeah.
I know you did a lot of the selection there.
Yeah. So, I mean, there's a couple different ways that you can make a hold down release mechanism. As Wesley was talking about, our first one was a shape memory alloy that basically, when you heat it up, it changes the shape in order to make the release happen. And the kind of the problem with that type of design is you don't want it to get too hot. Now you're starting to get into thermal limits. And if it gets too cold, it may not work as designed as well. So you get into these like temperature ranges on its use. The upside is that it's resettable. Like if you treat it properly, you can use it basically indefinitely from our standpoint. There are pyro type, which actually have little, not just brake wires, but they actually have a little, basically ignition circuits in them that will break bolts and that kind of stuff. And then the ones that we're using are fundamentally a preloaded bolt that goes through a cone mechanism that then is wrapped in two pieces and then is wrapped in a wire that when you pass the electric current through it, the wire will break. And then that releases the two-part mechanisms. They come apart and then the bolt slips out from there. So it's not breaking the bolt, which is a bigger shock event. It's letting the bolt go. And basically you're transferring all the force from being a high tension bolt across these two pieces to the wire is able to keep it together without having to take the full load. So it's kind of an interesting mechanism. The downside of that is that piece that breaks the wire is either very complicated to rebuild or you have to buy another one. So you only get like one shot per. And wherever it's installed, you now have to be able to reach to remove and replace it when you do the final release on the spacecraft. So
Now, they do make a product that's a mechanical resettable hold down release mechanism, and that's how we'll be testing mainly up until the point that we want to test, that we feel that we have built confidence in our deployment as a whole, deployment mechanisms as a whole, and the system fully built up, and then we can go and fire the more expensive.
Got it.
and ironically, the resettable mechanical version of it, that actually has a much longer lead time than the flight version. We've had the flight version for, after a couple weeks of ordering it, and we've been waiting a couple months for the mechanical version.
It goes back to show you, like, volume matters. I'm just going to keep repeating this. And when you have the resettable test, they sell those at much lower volume, so they take a lot longer to fucking get. And the ones that blow up all the time, or we cook or whatever, they make it much higher cadence.
Aside from just like the complexity of like how you actually test these, is there any trade-off when you think about all of the different loads that the panels are going to experience and that you have to test for?
Yeah, so all of these hold down release mechanisms have load limits. So you tension them essentially to the max load that they will see under vibration. And so if you surpass that, it will deploy, which is kind of what we saw with Odin. It was deploying on vibe until we corrected by taking out the spring. So yes, this was another trade that we went through that we kind of decided a long time ago to go with this specific hold down release mechanism because they had one of the higher preloads that we could use. Now, as the design changes, you kind of have to see, does this arrangement still work? Because currently we have one sitting in the middle. As we go through analysis and they say, hey, your loads are actually much higher than we were expecting before, or we saw in the breakout. Now we did a combined loads analysis, which is like where you put the whole entire structure in with the arrays and everything else. You're actually seeing way higher loads. Now we might need two. And so you have to split them up and figure out where to put those so that they don't change your packing density, is...
I feel like I just got a little bit of that. Tell them what you're going to tell them before you tell them, and then tell them, and then tell them what you told them. Like Wesley's like got the Ghost of Christmas Future over here going. Yeah, I totally caught that. By the way, you're not just letting that slip under the.
Yeah, what are you saying, Wes? Are we adding more?
I can't believe you don't.
Downs,
Yeah,
or
exactly.
Are we adding more panels? Neither. Correct answer. Okay, next question.
Great. Glad we got through that.
Yeah.
Moving on.
For protection of Wesley's future potential pit plan, we're just going to say neither and go from there. So like, I guess we learn from mistakes. Obviously, Odin didn't work well. Are there other famous like panel deployment problems that we learned from that happened with other spacecraft?
I mean, you mean like Hubble?
That was a softball question to ask for either of you.
Oh, sorry. Wesley, come up with another one.
I'm not the history buff here, so...
Matt?
Robin, you want to go? You go through.
No, you go.
No, I've talked enough on this. You haven't talked very much. Your turn.
Well, Hubble's was actually interesting. It was less of a deployment issue, more of a natural frequency issue. They were rollouts, and they ended up being so floppy that they started to wag in the day-night eclipse cycles and motion of the telescope itself. And so the telescope ended up moving while trying to observe, and so they ended up changing out the panels on really cool servicing Hubble mission space shuttle before you were born.
Yeah.
So you get to pass on that one.
Yeah. I mean, one of the first things that Armand, our head of GNC, had come up to me and told me was, hey, on deployment, can you make them as stiff as possible? And so that comes to the latching mechanism. So when you deploy, you want them to stay deployed, and you don't want them to flop around like a bird, because you cause all these problems for our guidance, navigation, and control team to point and be able to thrust in the right vector. And so we've kind of gone through a lot of iterations on that as well, on how the heck do you make a really stable latching mechanism for little to no mass. And so going through that, started with a basic door hinge and spring load it, and then see, okay, how does this deployment work? And the first one opened in 3 seconds, which causes a lot of loading and shock into your arrays.
Bad.
Yeah, especially with how heavy we are.
When you say open, mean the panel fully deployed in 3 seconds?
Yeah, the panel fully deployed in 3 seconds, so it's like snapping.
Yep.
It like looks violent on the test rig, and you're like, oh yeah, probably not a good idea. And we don't have like a 3-second timer to open, right? We have a lot more time to open.
No, yeah.
So no mouse traps is what you're going for.
No, it was actually like warping the sandwich panel as it deployed and locked out. So we sized those springs down. You actually kind of want that to be as long as you possibly can, as long as they can overcome friction. So you're looking at that for the spring sizing, but then springs as they deploy get less strong. So how do you actually clasp them at the end? So started with a natural kind of clasp where one piece just kind of slides over the other and then locks it down, and it can't pull back. However, you have a lot of play with that type of latching mechanism where you can still get flopping and the vehicle can flap like a bird essentially. So then I looked at some springs that had a canted angle and essentially looked like a circle, and then you would put a pin with a notch in them, and it would deform the spring and then create this compression force on that latch. And it's a shaped latch, so you can only pull it in one direction and you can't pull it the opposite, which seems like a great idea. Extremely hard to machine and machine properly, and these springs only come from one company.
Why is it hard to machine?
You're making, again, you're trying to go for the least mass possible, so you're going extremely tiny. And so the end mills for these are all custom and extremely tiny. So yeah, it's just not a fun project to even start with. Yeah, which
so we didn't do that because you don't know how to run the machine?
No. I actually went and I started buying them, and it was just it was going to be a lot of time and a lot of people that we talked to, and probably like 4 or 5 companies that we'd have to work with to get all of these parts to work together. So then we went to I was thinking about like, how can I make things stick together and not bounce ever? And I was like, well, if you throw 2 magnets together, they never bounce apart. So I inserted some magnets into the hard stops of the hinges and went and made like a little deployment mechanism, and it seemed to work pretty well. So sizing for that is still a little underway because you need to make sure that they don't bounce back. But the other problem is most magnets under high temperatures lose magnetism. So you have to find these special magnets called samarium cobalt magnets, which are on import control. And you have to get those to go into your vehicle because they don't lose magnetism over time or with high temperature loads. So this is actually done on a couple other missions. It's been done before.
So you didn't come up with that shit? You stole it?
No, I actually, so when I first brought it to people, most people were like everybody at the company was like, oh, wow, this seems pretty cool. And then Simona, our new head of structures, came in and she was like, yeah, I've done this before. So it's good to know that.
Let's try to pass this off to me as like, look at this cool thing I just thought of my own. Then to find out like 8 other people have done it.
At the time I did.
That's right. Yeah. I remember when you were walking around the floor with that, and I was like, that is actually pretty cool.
Yeah. And
this was pre-Simona being here. So
yes.
Wait, hold on. So then you just didn't do enough research?
No, I tried looking it up and I actually didn't really see anything for
You're not winning no matter which way you go on this.
But to be fair, like, I mean, how if this was a proprietary build, an internal company, like you could do research and not actually find any evidence of this, right?
Right. Yeah.
We'll chat GPT it later and see.
Okay.
I'm gonna throw him a little bail. And just let him
why don't we chat GPT right now?
Let's do it. Let's see how long Wes's pip is for.
Continue on while I.
Robin's gonna fact check you while we go through this, Wes. We'll see what's up.
All right. Well, while Robin,
What?
he's going to speak into it too.
Satellites use magnetic deployment mechanisms on their solar arrays.
Well, that might not be helpful because you could do magnetic-driven solar arrays as well.
So now you're gonna get picky.
Now he's gonna get a little technical. I think it is important to understand though the solar arrays themselves don't fail a lot. What fails a lot is the mechanisms driving them. I mean, you've had the failure. It's both the mechanisms and the actual accounting for them being deployed. It's very hard to deploy very big panels. There is, especially in low Earth orbit, but even when we're in space, there's solar radiation pressure. We don't call it an atmosphere. It's not an atmosphere. It's not a breathable, livable thing, but there is pressure coming from the solar system that's going to hit those wings at different angles. That's going to induce moments. It's going to be hard to control, and you have to go. And this is why when you build extremely large solar panels, they actually become very difficult to manage from an algorithm perspective. And so you kind of have this fundamental limit we see on spacecraft. It's around 25 kilowatts, somewhere in that range. We don't build spacecraft much bigger than that on the panel side. And the reason is it's very hard to algorithmically figure out.
What does
without a
25
lot of
kilowatts
structure.
translate to, like, dimension?
Big.
Okay. Thanks for that.
We're
I
true.
don't get me wrong. The International Space Station is much bigger, right?
Yeah.
But it has a much bigger truss structure. In fact, there was problems with the truss structure on it. It broke at certain points and has to be fixed. And that deployment to get out there, so you can not only, you have to think of it this way as like we're trying to put a giant poster in a little tiny Amazon package and ship it.
Yep.
And that's the challenge of how do you make that package automatically open and display the poster fully? It's pretty difficult. What did it say, Robin?
It said I needed to correct my query because Wesley was right.
ChatGPT 5 is really letting us down.
So far, the takeaway: ChatGPT thinks Wesley is right. Okay.
I think it's also important to note that a lot of these big EP systems also have driven solar deployment mechanisms. So they have a motor that drives these open, but that is also a ton of mass. So we had to go, or we decided to look at a passive deployment.
How did
mechanism.
Psyche do it? Was Psyche's motor driven?
Motor driven.
It was motor driven. Okay.
Yeah. And they also have a cross fold. So they have two that unfold out and then two that unfold the opposite way. So you actually have to do two deployment tests at the same time, which I actually looked at. And
That sounds hard.
yeah, it was not going to be fun.
Psyche's, I think Psyche's like 20 or 25 kilowatts. It's
It's
fucking
huge.
big.
Yeah.
It's not a small thing.
2,700 kilograms or something like that. So
It's a much bigger spacecraft, and to be fair, it's going much farther away.
I was going to say, yeah, that's the real thing. Is it's just further away.
well, when Robin gives you a budget of 2,700 kilograms, then you can
That's not happening.
never say never.
All right.
Maybe you
What's
want
the
to
cue?
keep the whole Astro.
What's ChatGPT have to say about Wesley?
I'm going to skip all the intermediate stuff here and get down to the literal. It says, bottom line, magnetic latching is a proven space mechanism pattern, but public flight heritage solar array use mechanical latches, not magnetic ones. In other words, people use it, but it's all proprietary.
Yeah. Okay.
Not
So
anymore.
That's why you need to act like China and steal.
Exactly.
Or I'd just like to say my bail that I threw you was directionally correct. All right. Last question for you. Any big, like, outstanding things you're worried about with solar panels before we transition to mailbag?
Cycling seems pretty hard. So like as you cycle from hot to cold, these deployment the deployment mechanisms kind of expand and contract at
Yep.
different rates. So trying to keep those all as similar as possible. But I'm excited to see that go through TVAC and start doing some deployments in TVAC.
Okay.
We should. There's one more thing we should add about solar panels, which is the overall architecture design of the panels. Odin, when it was curled up, at most could produce 30 watts of power on each side. That was not enough to stabilize the spacecraft or do anything on the spacecraft really whatsoever. I couldn't even turn on the full radio. Deep Space 2 is built to have almost 400 watts of power when it's folded up, which allows us to do most of command and control and even stabilize the spacecraft to some extent if the panels don't deploy. So we get this much bigger window where if we do have an issue with deployment, we have a whole bunch of attempts to fix it, which I think is a key part here. We probably could have saved Odin if we would have had the communication in that window, in that kind of golden window. But the reason we didn't was twofold. We fucked up the communication, and that golden window was really small. It's much bigger on vestry now, and because we'll have the panel facing out with that much power, it's actually almost extends indefinitely as we go out there.
Yeah, it's also the reason we have these big cantilevered wings that make us look like a TIE fighter.
That was for style.
right.
Yeah, what are you talking about? That's for style points.
Yeah. Star Wars sponsor us.
Yeah.
Yeah.
George Lucas personally is an investor.
Cool.
We should probably try that.
Does anybody have a connection to Georgie?
My wife went to school with his kids.
Georgie.
Chap, what the hell? Where's the intro?
Do you call him Georgie?
I've never met the man, to be clear. Like, this was also a long time ago, so go
Well,
ask her. Yeah.
Got to try. We're going to get
I
George
don't
Lucas
even
to
know where to
invest.
go with this.
I feel like that is just your tagline for the entirety of this whole podcast
It's
run.
very, very confusing.
All right, I'm going to remind you that you get to ask each of these two gentlemen a question after the
Why?
mailbag.
Why do we still have that segment?
Because
And
it's
why is it each of us now? You could ask one question at the end of either one, and now it's both of us?
you know, this is just a work in progress, man. All right, we are going to transition to mailbag, and I'm just going to get this out of the way. This is from Team Nuts, triple junction or low-cost silicon cells.
We're doing triple junction.
Explain the difference between the two so people understand what you're talking about.
I do not know what a low cost silicon cell is.
Okay.
So the triple junction is for efficiency. You have multiple layers that are for different wavelengths, and triple junction has the most broad spectrum of light that it can absorb.
Okay, cool.
And silicone is just an element.
Shout out ChatGPT
So-
for that one.
I didn't need ChatGPT for that one to say, like, I don't know what a silicon cell is. Like, that's just an element. So that's all we got.
All right, cool. From Everest, is Vestry supposed to be the final craft, or is there another mission set for the next craft? For example, Odin was mostly scouting. Obviously, the design will change over time and be improved, but curious if Vestry is a scaled-down version of what will be sent to mine, or is it roughly the same platform?
I mean, we are hopeful that it's roughly going to be the same platform, right? Vestry is, or Deep Space 2, I got to use my own fucking name, is a pathfinder for the follow-on mining mission that we will go attempt to do. Are there going to be some changes? For sure. But I hope that at a general way, if we measure in human bodies, it should be about the same. It should be about 1.5 humans, by, I didn't even get that right? Half a human by 3 humans long.
Right.
Yeah.
Yep.
That's still wrong, right? I think it's by 6
Yes,
humans.
you didn't even get that right. So
Okay.
upsetting.
Just to summarize that, Deep Space 2 is roughly the same platform that we will be using for
I like how
future
Robin
mining.
has just become like the grumpy old man on this podcast now. He's just like visibly angry over there.
What can I say? My face speaks loudly.
Yeah, it's not like we don't give him a lot of opportunity either.
I mean, seriously.
All right. This is from Bruce. Bruce says, I'm a little behind the power curve, so I just listened to the episode. Hold the link. Question regarding the two power amplifiers. Why a 20 watt and a 35 watt? I understand the use two different power watt amplifiers for A and B side because of the radiation concern for a product not typically flown, but why are they different power ratings?
I think I'll take this one.
By all means.
The answer is that the power amplifier is not the only device that has diversity of components within the link, within the radio chain. And so each device is optimized to take the input of the previous device and output it to the next device. So that's a lot of gobbledygook to say, like, our antennas are not necessarily the same. Our splitters are not necessarily the same. Our combiners not necessarily the same between the A side and B side. So the reason that there's two different power amplifiers is because the power amplifiers are sized for their particular side. Now, having said that, we're actually going through an engineering change right now where we're looking at the power amplifier output, because it turns out that, I know this is going to be shocking to everybody in the aerospace industry, but the spec sheets of performance of individual components do not always reflect reality when you actually run them through their testing in-house. And one of the components is coming in at a lower power in the chain, so we may actually change the amplifier to increase its output.
The other reason there is we also just weren't able to find two 35 watt amplifiers available that were disparate components.
Yeah, yeah,
Like, there
two disparate components.
Yeah,
Yeah,
there wasn't-
we
there
wanted
wasn't another one
diversity
available.
in manufacturers, diversity in component design to maximize our chance of not having a common failure.
Cool. And then last one, I believe, from Sam. What considerations do you have to make for surface charging that are specific to deep space? LEO satellites get away with exposed dielectrics because of the Van Allen belt exposure. Are there any benefits specific to deep space compared to Earth orbiting missions? What mechanism and structure testing do you do besides vibe?
Those are like 3 questions.
Yeah. There's more. I just stopped.
Oh, okay. The first one is
First one is
we have to design.
considerations for surface charging.
Yeah, I mean we have to design for the conditions. Every space vehicle has to design for the conditions that it's going to be operated in. So we design for deep space operation is the short answer.
Yep.
We probably would not do so well in the Van Allen belts unless we designed for that. And Wesley mentioned earlier on the episode the fine hairs that are inherent with carbon phase sheets, and those basically act like lightning rods for arcing events because they're really pointy. As an example.
Yep.
I'm not going to answer the third one because I feel like that's like triple dipping.
So you don't want answers for the one either?
I don't know what functional testing, thermal testing, vacuum chamber
What was
testing,
this third question?
combined thermal testing. We're going to go run the ion thrusters in a chamber as well to make sure all the avionics work. We do test the harnesses at high voltages to make sure there's no breakdown between wires. I mean, there's lots of testing.
Test everything we can in a reasonable and cost-effective timeline. I mean, I think it's really that simple, right?
Yeah.
There's a lot going on that we got to try to test.
Well, and just to help Sam out, his last question is how is our testing regime different than that of like say NASA or Big Prime?
Well, I mean, it's not in space.
The biggest difference between us and NASA is I don't have a whole bunch of congressmen trying to tell me that I have to go test in their district, so I don't have to fly my spacecraft to Florida to test.
Who's the
EVAC,
angry old man now?
and fucking
Seriously.
Georgia to test this.
Wow,
and
we
this
like
one to
swapped
test
roles
this,
over
and-
here. I went to being the reasonable one.
Fuck, it's so obnoxious. But I mean, NASA has these big. What NASA does provide is awesome science missions that are also jobs programs. And
By the
they
way, we have
kept
a
that
just
going.
just so you know. I mean, we have a Space Act agreement with at least one NASA center to utilize one of those really big national assets.
Correct. I mean, we can utilize those national aspects and use them. What I'm saying is that it's not Dianne Feinstein isn't saying like, in order for me to sign this, you have to go here and test here, and you have to do this part here and this part here, and that's how big NASA missions are done. I mean, look at the Senate Launch System (SLS). It's this conglomeration of people trying to get their little piece of the pie to keep their whatever their little jurisdiction full of jobs.
I mean, it's not that small. Like, I mean, Alabama gets like I think 40%.
Alabama gets 40%. I think is that the only? It's that and Walmart are the only income in Alabama, right?
I don't know.
Wesley, you got
You know
Arkansas,
what?
same place.
Wesley, you got any
No,
other questions
not
to
at
get
all.
us out of
Not
this?
at all.
Please. For the geographically challenged of us.
Yeah,
Bring
now
us off geography.
he's reassessing the question he wants to ask Matt. Like, what's the capital of Oklahoma?
Who cares?
Oh man,
Bring us out of this hole.
I care. Oklahoma's a very fine state.
Sorry, I'm so. Where I was that
You ever have
bad.
ribs in Oklahoma? Oh man, the
I've been
barbecue.
to Oklahoma. I don't want. Why would I go to Oklahoma? What's in Oklahoma?
Barbecue.
It's flat. It's like it looks like a frying pan, and it's just close enough to Texas that I don't really want to go.
Tornadoes?
Yeah, you can. I mean, it'd be cool to be like Twister. That's about it.
Oh, man.
So just to summarize this,
No,
you
don't
think
summarize.
Twister
No.
is the peak of what Oklahoma has to offer.
Why
this
else
country.
would you go there unless you're chasing storms? Like, why would you move to Oklahoma? I don't understand who wakes up in the morning and is like, I want to go to Oklahoma.
All right.
Wesley,
Yeah. Get us out of this.
what's your question for these guys?
Oh. Matt, why do you run?
Why is this the question I keep getting? As you get old, you have to do something so you don't fucking die.
No,
That's it. So I've chosen running. And so I don't fire everybody here.
On a serious note, what are your guys' biggest concerns for the vehicle as of right now?
Solar arrays. I mean, we just had a whole episode on it. Yeah.
That makes it your biggest concern.
Today. No, I mean, if I were to break down the risk matrix, to use aerospace terms, and looking at what the highest consequential failures are versus the probability that they'll happen, deploying solar arrays prevents us from really operating our spacecraft in any useful way. So, it has to turn on, has to deploy the solar arrays, and then, and honestly, after that, we can figure out and tolerate quite a bit. But if they don't deploy, we're just sitting in a really low power condition. Probably would not be able to use our EP in any effective way. It'd be ugly. The rest of the spacecraft, we have a lot of redundancy built into and a lot of graceful degradation, but, sort of like the rocket blows up or goes in the wrong orbit, you didn't even get started.
My biggest concern is that each one of the teams here eats its own bullshit and doesn't talk to the other teams. We see this all the time in engineering companies where you get in a bubble, you start to think about ways you could make your product more efficient, right? When it's on the solar panels, it's, oh, we love working with carbon fiber. Why don't we build it out of carbon fiber, right? You see this on science all the time. And as we go through it and thinking only to your team and not talking to the rest of the team about things that matter. For the solar panels, it's about like working with GNC to make sure we can counteract the deployment mechanisms and making sure we don't get into some weird oscillation in modes while we're in space. But it happens all over, right? It's also with avionics and with thermal and making sure everybody is aligned to what we're doing. That is what keeps me up all night. I think if we are to fail on Deep Space 2, it is going to be because we made a mistake internally with how we allocated our resources to the teams, and we let a team think that they were superior to another team and how they thought about a test. I think that is how you see big companies or any space companies really fail, is that. And so that's why I think you see us always going around asking questions and trying to understand what's happening in each team so we can pull that apart.
Okay. That's it for episode 30 of Roid Rage. Thank you for joining us, and catch us next week for episode 31, where we will have Jeff, who is on our perception engineer, talking about how we track stars. Until then, catch you next week.